In this problem, we will consider an L-shaped beam or an L-shaped frame subjected to a uniform load. The geometry is such that the beam is subjected to both torsion and bending. We are interested only in the deformation aspects of beam's response, so stress analysis is not part of the problem. So here's the picture of the beam. It is fixed at the wall, and we choose a coordinate system that is naturally aligned with the first bar, and the second bar is along the z-axis. The beam cross-section is a thin wall pipe, and our task is to determine the vertical displacement of the tip. So, to decompose this problem, we make a cut at B. So if I look at the free body diagram of BD, then in order to balance the distributed load Q, I need to have a reaction force, and I need to have the moment. The moment is about the x-axis. This moment, as far as BD is concerned, produces bend. Now, if I look at OB, this moment is no longer bending. It's a torsion moment, and the torsion moment is clockwise, or it is negative with respect to the x-axis, and it's probably not that difficult to see that it is negative, because if you think about the action of the distributed load on BD, you will clearly see that this distributed load induces clockwise rotation about the x-axis. So now we can look at BD, and now the moment appears in this form, and it clearly shows that this is a negative bending moment, right? But it has the right direction, so the answers are straightforward for the shear force R and for the couple, and the values are given here. So the beam BD experiences bending. Now, if I look at the beam OB, it experiences bending due to the distributed load Q and the force at B, QL, and it is subjected to torsion by the couple QL square over 2. And so we will analyze bending and torsion separately. So for bending, we have two loads. So the first table comes for Q, the second table comes for the force at the tip, and if we use superposition, we could see immediately that the displacement at B downward, this part comes from this table, and this part comes from this table, where of course P is replaced with QL. Now we can proceed and analyze torsion. So torsion induces a clockwise rotation, and this rotation is calculated by the formula TL over GIP. And I don't use any minus sign, I just simply keep in mind that this rotation is clockwise about the x-axis, and the only thing I really need to do is I will replace t with ql squared over 2. Now let me proceed with analyzing BD. So if I look at BD, I can think about the following superposition. First, I think that B is fixed. Then I can think about a cantilever beam of length L subjected to a uniformly distributed load. Then I say, in reality, B is not fixed. Why? Because it undergoes rigid body translation, right? Because the point B moves, and that's VB, plus the twisting angle at B, when we look at OB, translates into a rigid body rotation of BD associated with bending, and that's how it's shown. Right, so this is phi B, okay, and this phi B is because the beam OB twists. So now we can do the following superposition. This result is from the table for a cantilever beam subjected to a uniformly distributed load plus VB plus phi B times L. And now we can bring VB and phi B from previous slides, and that's how the answer looks like. Finally, we just calculate the moments of inertia using, these are exact results, and these are approximate results based on the assumption that D is much larger than T. The way I obtain these approximations, I expand both terms, and then I neglect the terms that are t squared, t cubed, and t to the 4. I only keep the term that is linear in T.